Yes, sir. Yes, sir. Visible, sir.
Okay, no?
Visible, sir. Yes, sir. Yes, sir.
Can I speak now?
Yes, sir. Yes, sir. You can speak, sir.
So let me just give you some overview. There are, whenever we do AI applications, first we have to see what kind of data we need to handle. Am I audible now?
Yes, sir. Audible, sir. Audible.
What kind of data we need to handle? High performance computing is one, high throughput computing. Both are completely merged last 5 years because of deep learning AI. So let us see what is high performance computing and high throughput computing. That is one side. Let us also know programming paradigms like OpenMP, message passing, GPU, a lot of things are there. That also will come to know. So computing depends upon speed, how fast I can do computations. That means how fast I can do floating point computations, how fast I can do searching. Floating point means how fast I can do car crash simulation, how fast I can do weather simulation, how fast I can do some of the medical image processing. That means how many floating point operations you can do on your laptop, which may be dual core, quad core, or 8 cores. That is one side. Second thing is fast data processing. That means if I have dual core or quad core or the 16 cores or maybe 5 and 12 cores, how many jobs I can process? In other words, how many processes I can do or how many threads I can employ. So threading is one, process is one. So we should know about threads and process, because when you have large amount of data, what each thread is doing, how many threads I can process in a given amount of time. Similarly, how fast I can do computing operations. So both are also very, very important we need to see. So that means don't worry about the programming paradigms. More worry about maths, modeling, and system. That is important for the AI because huge amount of data we need to train. And when we get the training is over, we do it. But when we do training, are we doing 2 hours, 3 hours, 10 hours, 2 days, 4 days? Are you doing 1 million parameters, 2 million, 10 billion, 20 billion? How we can do? So that means more focus is on math model and algorithms. The programming paradigms which are there, they keep on enhancing the programming paradigms. Let's see. So floating point means raw speed. That means one is how much performance I get by running a program on dual core or quad core laptop, or if I include 10 systems, 20 systems, 1,000 systems, then how they are really connected, how I can distribute the work, and how I can get the speed up. All these things are also important. That's how the high performance computing called raw speed. How fast I can do operation. That means, for example, launch vehicle simulation. How many number of complete the launch vehicle simulation? Maybe 4 seconds. Car crash simulation. How many number of processors I use to simulate the car crash? How fast I can accurately predict the weather for every village in the Bay areas or in the some of the earth sea areas, and how many number of systems I use. These are all come under the high performance computing. So that means we need to think parallel. The fundamental thing, we need to think parallel. When you think parallel means either program, can I use OpenMP, what our earlier speaker conveyed? Can I use the message passing? Can I use operating system POSIX threads? So these are all important. So that means one way you need a fast processing of data, fast processing. Second way is that you need to process a large amount of data. Both are equally important. So how your laptop with the dual core, quad core can be used, that is important. Second one is high throughput. High throughput means number of tasks I can complete in a given amount of time. Each task size may be different. Each task memory may be different. Whether you can do tasks, maybe OpenMP, maybe use POSIX threads, maybe use MPA, message passing library. So all these things are very, very important to understand from the problem point of view. So that means high performance computing, high throughput computing, how they are really driving the AI applications, that also we'll understand. So to understand high performance, high throughput, we need to get new nomenclature and new terminology also we need to understand. So what is our objective is performance, which is required for the AI training, throughput, more number of tasks, that is more number of threads, more number of processes running. How we can do? Either one, we do parallel processing. Second one is distributed computing, where the systems are geographically scattered and you collectively use all the sets of systems and to run a single application. So these are also come under the what kind of this parallel processing, what kind of the distributed computing system. They also come under the shared memory, nothing shared or distributed shared memory. All things also we have to understand. That is when you understand all the things, we can do AI training more efficiently actually. So for example, to to get complete picture of all the things, first we need to know parallel computing, what you call multi-threading, whether you can do multi-threading using OpenMP or you can do multi-threading using process level. All these things we need to understand. So let us go through details. So what is meant by parallel computing we need to know. Parallel computers consist of hundreds of processors are now commercially available. Good example is your laptop with quad core, you have 4 cores are there. And then all these 4 cores effectively you have to use. In sequential computing, you do fetch, store, compute, whereas in the parallel computing, fetch, store, compute, communicate, cooperate with them. What the earlier speaker talked about OpenMP. OpenMP is a compiler pragma. You put compiler pragma in a for loop of your program, it automatically takes all the threads, look into the for loop variables, for loop arrays, all the threads concurrently access the shared data and they compute and they store the output privately. That means every thread generates the output privately. All the threads are running on a single system. Single system having maybe 4 cores, 8 cores. Then OS also will intervene. So that's how the compute, communicate, cooperative game. So that is what called the shared memory programming. Let us see. Good example is how to stack books in the library. There are many ways you can stack the books in the library. One is single worker is there. Single worker wants to accomplish the task of stacking books in the library. It takes long time. Then I employ more workers. So what is my objective? I have to accomplish this task using this many number of workers and ensure that every worker takes equal amount of time to complete the task. One way is you divide the books among the workers and every worker stacks the books at one at a time. Second way is that you can assign disjoint base in the library to each worker. Each worker collects the books and keeps at the exact location. One approach is N is the input, P is the number of processes, N is divisible by P. That's what work is given to everybody. Second one is another approach. Both the approaches are basically want to accomplish the task in a given amount of time using this many number of workers. So that means you are looking for performance, you are looking for efficiency. So for all these things, we need to understand the parallel programming. When you do parallel programming, we understand the performance. When you understand the performance, we get a speed up. Speed up means how fast you can able to solve when you use 2 workers, 4 workers, 8 workers. If we are able to solve problem much faster, the AI training becomes less time to complete the work. AI involves huge amount of time you spend on training. The training runs on 1000 GPUs, 10,000 GPUs, and then all these programming paradigms we need to understand also. So let us see what these clusters look like, what are the issues. My colleague also discussed, my other colleagues also will discuss these things to get idea. What I'm trying to say is that, so these are all clusters. If you really see these clusters, every system is a dual core or the quad core laptop, and then it is also called uniform memory or the non-uniform memory. Every system is having also accelerators. So we collectively use all the systems here actually. So that in this diagram, if you see, every row has got nearly 16 nodes are there, and you have 6 rows are there. So 16 into 6, 96 nodes. Every node may have 4 cores. 96 into 4. That means somewhere near about 350 cores are available to solve the large problem. What is a large problem? In the case of AI, it's a training, forward propagation, back propagation, weights update, all these things, class function, everything we have to do parallelly actually. So this is one example of cluster. Now let us go more details. Now cluster look like this, a front end node, and there is the interconnection network is there. There is a parallel file system, huge amount of data. When you generate in AI, that data resides in the parallel file system. Every compute node access the file in the parallel file system. When it access, you need to write very good programming using MPA or the message passing or the Hadoop MapReduce. In every compute node may have the GPUs. So this is how the abstractly. So what is interest for us is how much computing I do on every node. What is the cost of communication in the across the nodes? What kind of routing algorithm I use? How much memory required to compute? All these things also very, very important to understand when we do the AI applications. So today, many applications, they take 2 days, 3 days for AI training where they use 10 billion parameters, 20 billion parameters. How much the total time can be reduced? That means you need to design good algorithms and good libraries. Let's see. So here what you see is that we have a example, a large switch is there. The switch has got first level, you have the 16 port switch, 8 are connected to the 68 host, and above also 8 host, and each host is 8 cores. So 8 into 8, 64 cores are there. So you have 5 first level switches, and one second level switch is having 40 ports actually, because there are 40 ports which you can connect everything. That is how you can build a large parallel computing systems actually. Now the question comes, how do we use it? What program paradigm and how AI training can be done on this? These are the issues. Am I audible now? Going okay? Hello? Hello?
Sir, yes, sir, you are audible.
It will be, thank you very much. So now let's see. These are the kind of systems which we build in CDAC Pune. Last 6 years, we have been given more than 20 systems. They all IITs and many research institutes under the NSM, where the DST, IISc Bangalore, CDAC, MIT, they are actually involved in designing the overall CDAC duty is to get the processes, integrate, develop the tools, middleware, everything is also one of the activity. Now, question is, when I go back these systems, where we need to focus here, where we need to focus. So that is important here. Focus, we need to understand from AI point of view, how much data we are moving. What are the kind of memory? Memory means every compute node has got 2 cores, 4 cores, 8 cores. 2 cores share L1 cache. L1 cache is high-speed memory sitting on the chip. L2 cache of the chip. L3 cache, all the cores are sharing in one cache. How fast we can move the data? What kind of which memory is there? The data. All these things are important to reduce the overall training period. So this is very important. Memory bandwidth. If you have 2 cores, if you have 4 cores, if you have 8 cores, if you have, for example, 8 cores, I can launch 2 processes and 4 threads each, total 8. I can launch 8 processes. I can launch 8 threads. Every thread is doing some kind of convolution neural networks in the AI. Then how fast we can move the data from memory to CPU, memory to each core, and how much bandwidth is really there. This is also very, very important. So that means tomorrow when we do a training on 100 systems, 200 systems, or we are running on 8 GPUs, then we need to understand the and GPU memory latency and how the computations can be. That means how many bytes of data are required to do this floating point operation, how fast I can move my data to CPU, because you have 2 cores, 4 cores, 8 cores. All these core CPUs, they're waiting for the data to come. That means how fast we can move the data. That is also very, very important. So that means, see, these kind of systems, you have every system is 16 cores, 32 cores. Your large amount of training data is there, distributed training. Data is distributed in every node. Every node is having 8 cores, 16 cores. And have to compute. When we want to compute, we need to know what is cache, cache, main memory, bandwidth, how fast processor can do. All these are equally important actually. So now let's see. Now come back. What are the issues I need to address? One is every system may be shared memory. All the systems together as a cluster. Then if I go to the weather data, entire weather data, you have the cells in X direction, cells in Y direction, and then height, longitude, latitude actually. So now who is going to partition the data, make it available in every system? Is data is partitioning or computations also partitioning? How to map data to every node, every processor? How do we do synchronization? How do we do communication? If N is a message and if you have P is a process, to how much time to take scatter? Scheduling. One of our speaker talked about scheduling. Maybe tomorrow I will talk about the scheduling more. How to schedule job, because you want to do a training on 128 processors. Somebody requires to do training on 512 processors. And how do you really schedule the job? So these are all very, very important when we do the real AI training actually. Ultimately, we want to accomplish the training in shortest possible time. How do we do it actually? So now you can see how the systems are now designed today. CPU training. What you see is a multi-core system. Each one is a multi-core system, 2 cores, 4 cores with 8 GB memory. Second one is same system is CPU on a single chip. That means you can see GPU memory, GPU can see CPU memory, unified memory. GPUs are very fast. That will learn a little bit after some time. So that means there is a change in the hardware happening continuously to do the AI training much faster. So that's what we need to understand. Where I am running a program, I am running a program on the CPU ecosystem. I am running on the GPU based multi system, or I am running on FPGA based multi-core system, or I am running on a cluster where every node is a CPU, GPU. All things we have to understand. That's why today AI architecture is driving the industry. AI computing is one AI architecture. That means what kind of systems, what kind of network, what kind of processor, all things are also very important in HPC. Now what we do, we go back again. We'll quickly see what is the each node here, each compute node. Let us see. Today we have that CDAC. We have systems with 1,000 cores, 1024 cores. That means 1024 cores. That is called multi-core, 32 sockets, 32 core, 1024 core system is available. It has got single address space. single operating system, and we can do computing. And if you take hyper-threading means two threads running on a single physical core. Every physical core processor has got two logical cores. If you have 1024 cores, that means 2048 are there. 2048 threads you can run single memory, single space, you get tremendous amount of performance. But what is our work is what each thread will do, how the thread synchronization is done. Is the threads are computing matrix computation, what way the threads are working on the AI training. These are also very, very important. Now let's go to the each thread, each system. Simple example of quad core laptop, which you see. So 4 cores, you can run 4 OpenMP threads, or you can run 4 POSIX threads, or you can run 4 MPA processes. MPA is called process level. OpenMP is called threads level. So we need to understand both the things very, very carefully. When you have 4 threads, fine, it's very easy. When the hyper-threading enabled, 4 cores become 4 physical core becomes 8 logical cores. So totally you can run 8 threads. But today I'm having 1024 cores. That means how the threads can employ, how threads can synchronize, how the live locks can be handled. All things also very important in the programming. So now question is whether I have the 4 cores or 8 cores or 16 cores, how many floating point operations I can do in one clock cycle. Floating point operation means single precision, double precision, how much you can do. Next is, if I have 8 cores, 8 threads want some data, how fast I can move data from memory to CPU. Now I told you that there is L1 cache, hierarchical memory, L1 cache on the chip, which can access very fast, maybe few nanoseconds. L2 cache of the chip, it takes more time. L3 cache, more cores can access, and main memory. That means there is a hierarchical memory is there in today all the systems. We need to understand what kind of computation I am doing, what kind of memory required for every thread. All things also very, very important. So let's see. Now that means you have multiple GPUs in a node, every GPU has got streaming multiprocessors. How many streaming multiprocessors there in GPU? How the GPU scheduling is done, that is called warp. That means 32 threads is grouped as a one warp in the GPU. All 32 threads execute one instruction. That means all 32 threads take equal amount of time to do convolution neural networks. You get 32 times speed up. But is all 32 threads take same amount of time to access the data? Where the data is there, how fast we can move the data, all these things are challenges. Each warp consists of 32 threads. All 32 threads, how they really work the instruction execution, data getting, all these things are also challenges. Okay. So we have the today, maybe in another 2 years time, you have multiple socket multi-core system. That means I have 16 cores on my laptop. We have 2 sockets. One socket is 8 cores, another socket is 8 cores. Socket to socket communication and core to core communication. And I showed you many cluster, many nodes are there, node to node communication. So all these things are also now is going to change quite a lot to get this of the training actually. So now this is how they look like: multiple sockets, multiple cores. That means here you have the 16 cores, then you can able to do AI training, and every node you can have the GPUs also. So that's how the shared address space. So that means shared address space means shared memory available in every node. How effectively you can use actually. So this is how. So that means what is most important is processor is a hardware, process is a job which you're running. Every process memory is private. Every process can launch many threads. All threads belong to one process. So process level, threads level, parallelism, this is also very much essential actually. Today you can see in this diagrams 12 CPUs are there, and you can launch some processes on CPU 1 to 4. Some threads can run on the CPU 1. All these things we need to understand more about the system also. Another issue is that you have a large amount of data. The data is in the storage. We need to access the data. That is called IO operation. So how fast you can read the data, write the data, how many threads are involved. That means you have the main memory bandwidth, you have the IO bandwidth. That is also we need to be very, very careful. More data in IO means CPU is not doing anything, you won't get performance. But if more data is in the memory, you can able to access much faster using threads. So how to intelligently write a program where the huge amount of data is in the storage, we need to get the data in the storage. How to do it? This is also another issue. That's called IO bandwidth. Now let us see. This is how the shared memory look like. A simple system, uniform memory. You have different level of caches are there, and you have shared memory and main memory. So here you run POSIX threads or OpenMP or the API processes. These are very, very important to understand the abstract view of the system. Now let us see. Hyper-threading enabled means what? If you have a quad-core processor laptop, if you're running Ubuntu operating system, then when you install Ubuntu OS, when you run Ubuntu OS, every physical core has got 2 logical cores. That means you have 8 logical threads are running. Virtual cores are 8 threads are running. How the threads are basically spawned onto the every CPU. Some scheduling will be done, OS scheduling will be done. How the tasks are executed. So these also very, very, very important. The picture clearly shows that many applications can run on the big system with the 1024 cores, where by employing hyper-threading enabled, you get 2n threads can run on the overall system actually. So multi-threading, you can achieve multi-threading. OpenMP is called high-level parallelism, which I will tell you about it later. Now GPUs. So the GPUs are basically accelerators, which are sitting at the 16x. Every system is having PCA 16x slot. The PCA 16x slot, you can put the GPU accelerator. You can transfer data from host to CPU to device GPU, and you can run on the GPU programming. Now today, CPU, GPU on a single chip. You can see GPU memory, GPU can see CPU memory, completely unified memory. For all AI applications, all the systems are coming with CPU, GPU on a single chip. Now let's see, what is the advantage of the GPU is when you run on a program on CPU, you have the control unit is there, and you have the cache is there, and you have AL is there, and you have DRAM is there. So much amount of every component plays a major role, and it takes long time to run a program on the CPU. That CPU you cannot have more number of cores actually. You have dual core, quad core, 8 cores. That means more and more transistors cannot be put on the CPU very easily. But CPU has got the file transfer, security, everything is there. On the other side, GPU, all arithmetic logical units are directly addressed to the memory. Because ALUs are directly addressed to the memory, you can do much faster in computing. And also, GPU memory, CPU memory is very, very less. That I'll show you here. Maybe I just show you here. I'll come back and show you. Yes. Here you can see CPU memory is 100 GB memory bandwidth. That means I can't launch maybe 8 threads, 16 threads, 24 threads on CPU. Each thread requires more memory, very difficult. Whereas the GPU memory bandwidth is more than 450. Because more than 450, I can launch 1 million threads, 2 million threads, 4 million threads very easily. That is how the AI requires a lot of threading. And also I'll tell you, presently you do 32-bit, 64-bit computations on the CPU, whereas in AI you do 8-bit, 16-bit. 8-bit requires 1/4 of the memory compared to 32-bit. 16-bit requires 1/4 of the memory compared to 64-bit. So 64-bit, 32-bit has been reduced to 8-bit, 16-bit computations in the AI. That means more and more, instead of 2 lakh threads, every thread does 64-bit computations. Now I can launch 8 lakh threads, every thread is doing 16-bit computations. So that means what? when you do AI, the computation called mixed precision computation is also happening in the AI. That's where GPU with the used memory bandwidth, you can launch 1 million, 2 million threads to get the performance actually. So let us see how it works. And I give you a little bit overview also so that the concerned person will come and some other speaker will talk more about the GPU programming. Now, GPU also has got some libraries. Nowadays, many of the devices you have high level programming where you don't have to write complete program. You use some high level API where you can able to get the program running on the backend system. But to get performance, we need to know all these libraries actually. So there are many ways to do the programming on the GPUs. One is NVIDIA GPU, other is AMD GPU. How we can do, we'll learn also. So GPU is CPU launches all the data of the AI training. Once the data is launched on the CPU, it launches GPU threads and data is moved on to GPU, and then GPU uses more than 1 million, 2 million threads and do the computation. And after the computation is over, the data will again move back to the CPU. The question is, what kind of computation are doing on GPU? That means good example of GPU in analogy, typical Kerala boat race. In the Kerala boat race, manager gives one instruction. All the 32, they row the boat. All 32 persons take equal amount of time, equal amount of memory, and they do the job. Single instruction, multiple data. All the work is highly independent chunks of computation. That kind of work should be there in your AI application. By default, AI are doing 1 billion, 2 billion, 3 billion parameter training. Then some training can be done parallelly on the GPUs. That is one thing. Second thing, earlier we used to do 32-bit, 64-bit. Now we can do 16-bit also. By doing 16-bit, you can launch double the threads. By doing 16-bit, you can save a lot of memory. So one way you gain in memory, other way you gain in computation speed up. So both will be advantage on the GPU. That's where what we do on GPU is data parallel computations. Good example is the Kerala boat race. Maybe many other examples also there. So what is important is how that somebody will discuss in the future, which I'm not going more details. This is how the GPUs works, where CPU is launched on the host system, and when CPU execute, it launch a kernel. Kernel has to be executed on the CPU. One grid is launched. Grid consists of kernel. Kernel consists of bytes. That's how it operates. So this will be discussed in more details by each going. So now we also have the other programming on the GPU. Similarly, OpenMP, we can have the OpenACC. That means I put one statement, automatically that blocks that it runs parallelly. So that means the entire GPU high-level programming is there, low-level programming is there. In CPU, high-level programming as OpenMP and low-level programming pthreads. So all these things are very, very important to understand actually. I just skip some things, but like let me go to the other things about the. So now MPI library, one of my colleague also discussed MPI library. How the MPI library is there also equally important. For example, you see how the MPI library is there here. Here you have 8 nodes, 16 nodes. Each node, all the nodes are connected by different kind of networks. You have the scheduler is there to run the jobs on 2 nodes, 4 nodes, 8 nodes. And you have the network routing algorithm is there. So this is there, and your programming paradigm running on NPA. NPA is the library which you can club with Python, MPA with C, C++. MPA is exactly same as the post office analogy. Post office is just, if you want to post a letter, sender address, receiver address, sender address, source, destination, same analogy is there in NPA library implementation. So let us see, this is a simple cluster consists of the nodes where you talk about the programming, where I talk about the AI training, somebody talks about the storage, Somebody talks about the networks, routing algorithm. Somebody talks about scheduling. All these things are the part of the HPC. So if you have such kind of HPC system, you can do AI training much faster. So what we need is that, let us see, I give more complexity here. Exactly same as the MPI, exactly same as the post office thing. Here we have when you post a letter, how the letter goes to destination, which is to be, it all has different kind of. Your duty is to put the letter in the mailbox. Post office will take the letter and go to the receiver's mailbox and go to the receiver post office, go to the receiver mailbox. At all the level, you have the high layer, middle layer, lower layers, everything is there. You can also, same thing, we can talk about the OS level, application level, presentation level, access layer, transport network. Part of the large distributed computing network. Now, complexity, I put GPUs also. I put GPUs for every node. That means today, AI training means the deep seek AI, just like Chat GPT, OpenAI, deep seek 2048 nodes, 256 nodes they use. Each node is having 8 GPUs, and every GPU is having 80 GB memory. Your laptop is having 2 GB, 2 cores, or 2 GB, 4 cores, total 8 GB. But what I'm saying is every node has got 8 GPU, they call GPU blades. And every GPU is having 80 GB memory. That means if you have 256 nodes with 8 GPU, total it comes 2048 nodes. Overall 2048. So what I'm trying to say is that so 16 cores. Every node have 8 core CPU. Every node have 8 GPUs. Every GPU can launch 1 million threads. So totally large number of threads which are running on the CPU and the GPU. That's how the AI training is there. Now, what are the issues? Issues is challenges, scheduling, networks. Networks means how we can communicate one process to other process, one to all to all processes, scattering data, gathering data. N is the size of the data, P is the processes, order of NP, order of N log P. And networks, you have the OS layer, TCP/IP. Programming, you have the OpenMP, you have the MPI, GPU programming, you have the Hadoop programming, you have the TensorFlow. Where the data? So that is how the complexity is there in the HPC system. These are all extensively used in the AI now. Come back to the IO. How much data which I am really storing, how the AI will take the data and predict the future terabytes of data. How all the data, how parallelly you can process. That is called parallel IO, threading IO. In the HPC AI. So what is the programming paradigm? Programming paradigm, I give 10 minutes, open and close it. So programming paradigm means if I have single node, 4 cores, 8 cores, I can go POSIX threads. Or if I have a performance with GPUs, I can go POSIX and GPUs. That is a low level. OpenMP, one pragma, high level. That means if it is assumed that by putting one pragma parallel for loop, then the for loop which is there automatically running on the multiple CPU and get the performance. But the for loop inside, we need to see the computation is independent or computation is dependent or there is a dependency there. All things we need to understand also. This is called low level parallelism, high level parallelism. Today, you don't talk about high level running the entire library. In the case of the API, it is write API in last 4 years. Now you go to directly ChatGPT, DeepSeek, it does everything in the background. So that means lower problem 10 years to 15 years ago, come to high level and open CPU. Then they got one API, I write one application for API, that is do parallelize, automatically it will do on CPU or GPU. But now one API has been replaced by the complete AI, Chat GPT, OpenAI, DeepSeek, and all these things. So there is a shift in programming paradigms. So what is your responsibility is which power model we have to use, what kind of system we have, and how do I use my system on side. But today, 90% of your application is math modeling and algorithm and which AI need to use, which AI tool, ChatGPT, OpenAI, DeepSeek, as well as the Q1. Out of all the things which I should use to solve my problem, how I can able to communicate my problem in a. That's what we always say. Good programming language is no need to learn Python. You learn good English, then automatically you get good Python code. That means there is a lot of speed up. There is a lot. Your learning curve will very, very, very fast if you really get used to the some of the AI tools in future actually. So now you see, you amount data, then you have the Hadoop MapReduce plus HDF system. Google uses MapReduce and Google File System. NPI uses parallel file system. Then you have Java threading, Java GPU, Python threading, Python GPU. So all things are now available. But after coming out with the OpenAI ChatGPT, things are changing very, very fast. So programming paradigm on one node, low-level API, high-level API, OpenMP, POSIX threads, and threading building blocks, C, C++, Python, that's one side. But all the systems have GPUs. If you use NVIDIA GPUs, you use programming or OpenACC. If you use AMD AMD systems, you use OpenACC. If you use Intel-based systems, you use SQL. So that means every vendor is equipped with all programming paradigms. What we need to do is more about a training, a math model, a algorithms only. Rest is available now. So there is a shift in thinking for everybody. So they need to understand all the things. So now let's go to the other slide and I'll close it. That means whether I do on a single system memory, whether I do on a single system with the GPUs or multiple GPUs, or whether I do large cluster where every node is CPU only, or every node is having CPU, GPU, or in future every node is CPU, GPU by itself there on the chip. In 2 years' time, all the cluster and AI will have the CPU, GPUs there on every node. Then data is very used. If you want to do AI for the teletraffic application, which I'll cover, use every 2 minutes you get 10 MB of data in teletraffic. How do you really process the data? How to partition the data, how to map the data, and how do you synchronize the data, how to communicate data, programming APIs, your distributed computing, distributed TensorFlow, distributed AI, Spark, Hadoop, MapReduce, and you have the machine learning, deep learning AI application will be there. And what is the left side is programming, low level API. That is, I go at the OS level and try to run on my threads and get performance. High level API where I simply run OpenMP threading. Very high level where I just complete frameworks will be there. So these are the moving. These are the different programming patterns which are there. I'll skip actually. So lastly, I cover 2-3 important slides in application. Maybe I take 5 minutes more. Am I audible now, everybody? Am I audible?
Yes, sir. It's clear.
So let us see how the applications have been defined. One is somebody looks AI application training is performance. Somebody says I need large amount of AI data, so I need scalability. Means I need to accomplish large amount of data processing in given amount of time and given this many number of processors, and how do you get scalability? I do only compute, or if I do more AI training, I need IO also, more amount of data I need to process. If my application uses more memory for teletraffic application, more memory, or cache friendly means for weather applications I want to do compute. When I do compute, I'm using L1 cache, I'm using L2 cache, and if I have large number of nodes, Google uses more than 4,000, 6,000 compute nodes cluster, then what is the communication in internode, extranode? And also how the network scale, how many GPUs are there, is AMD GPU, what is the programming paradigm, NVIDIA GPU, what is the programming paradigm, Intel GPU, what is the programming paradigm, which API, I use low level API, high level API, this is how the HPC is now changing actually. So I will just quickly cover some of the applications and then close my talk. So what is more important in the AI training is how the hardware is really driving, how the firmware is increasing, how much complexity in 1,000 nodes, what kind of operating system runs on every node, how the networking really works, that is store and forward routing, cut through routing, how the compiler, my colleague discussed about the compiler, GCC compiler, ICC compiler, NVIDIA compilers, AMD compilers, IBM compilers, linkers, OpenMP pragmatic compilers, libraries, which library I can run which gives 10 times, 20 times performance. And libraries also I can design on the one system, 10 system, 1,000 system, how the application software. All means intelligence is only in software, not in hardware. Hardware is a dump. Entire intelligence is in software. Software means mathematical model, algorithm, libraries, which we have to design in the future. The data is very, very huge. So let us take some 2, 3 applications. Big data statistics, telecommunication. Every day we process more than GBs of data. Finance. Every 1 minute you see many financial transactions. You get 4 cores, 8 cores, 16 cores, how the future generation manufacturing, especially mobile technology as well as the processor technology, quantum computing, all these things, nothing but different applications have different requirements. All AI should able to address what kind of architecture you require. That means what? Originally 10 years ago, you have a simple HPC system. Today, you have HPC system, different data, amount is high band, how much pump across compared to all computing. Real-time response for the data, how the network is playing a role, how the country. These are all challenges in the present era of AI. Require most powerful HPC system. Why complexity and tomorrow it is how the programming stack. So so the question is when
Sir, audio is not clarity, sir. Sir, VC Rao,
all
sir.
things are very, very important.
Hello, sir.
And then
Audio is not clarity, sir.
I just quickly cover.
రావు గారు మీ వాయిస్ బ్రేక్ అవుతుంది. No, not clear.
Signal issue, sir. Signal issue.
Three, 4 slides. If you see this picture, when I do AI training, I can do applications. I can do as the telecom data or the finance data. When I talk about the telecom data as well as the finance data, as well as the enterprise applications, how much network bandwidth play a role, how much network latency play a role. In the case of AI training, how the IO operations are done, how many threads I used to concurrently read, how many threads I used to address the burst data transfer. When I do weather application, how many floating point operations I do in one core, how many cores are every node we have, what is the memory capacity, what is the memory bandwidth. What you really see, the green, red, blue, that is basically every application, whatever requirements from telecom application, whatever requirements from finance application. If you go to the agriculture application have many devices, sensors, actuators, all the sensors, and rainy season, monsoon, dry season, summer season, winter season, all these things, nothing but heterogeneity, complexity, IoT devices. That is also part of the AI. If you see right side in this picture, that's how my system is there. Cluster of nodes, every node having GPU. So that means all these things are doing batch processing earlier. But telecommunications, we don't do real-time operations. We have to do processing for telecommunications. That means batch mode processing, scheduling, which are part of the high-performance computing. Now changes are happening very fast because we need 24/7 real-time operations of running the many chemical plants, many oil industries, telecom service, finance service, banking sector. That is also come out of the digital twin. These are the algorithms, applications we need to understand: graph theory, statistics, linear algebra, machine learning, deep learning, probability flow libraries. All these libraries are running on the different accelerators, different GPUs, different nodes. Then we need to have a unified software stack to address this problem. That is also part of the AI. That means today, when you go to chat GPT, you process many queries. All queries have different type, different codes, different thing, everything you are able to get solution. That means in the backend, distributed computing, GPUs, programming paradigms, everything happens actually. So I'll quickly close it, last two slides. If you really see, one way astrophysics application left side, other one is bioinformatics application, one is that drug design, and other one is that massive data on the astrophysics. Third one is real-time information about the data mining. All these things are nothing but data is heterogeneity, data quality. How do you find out emerging communities to mining algorithms, and how we can handle? So how the data is distributed, how the computations have been partitioned, how the data is distributed, how do you do synchronization, how do you map this data, and how do you communicate. All these things are basically important. Other one is how the data is stored, how data is moved, how data clustering is done, how data analytics is been done. And if you really see all these things, we use graph theory. When you use graph theory, we talk about the shortest path, direct, indirect graph, all things we need to see. So this is how the data is changing. This is how the weather simulation. We can see in entire weather simulation, what is important is you want to find some patterns of the data where the cyclone is very effective. That means high pressure, high tidal waves, you need to measure. That means there are so many cells which are there, and the entire region is divided into many cells, about longitude, latitude, and then height also. With this, you can able to have, if you take 104 tells in X direction, 104 tells in Y direction, if you take 100 meters size, that is called 100 MB of data. 100 MB, 1024 into 1024, 1 MB into 100 meters, 100 MB. 100 MB data, you need to find some patterns. That means it's called search algorithms, how effectively we can do. What happened to the future weather prediction, how AI can be useful. These are all the areas which we need to work. Lastly, telecom, finance, banking, railways. These are all real-time data which is moving 4 bytes, 8 bytes, 16 bytes, and all the data we need to simulate. So that's how we can see one up. So how the real-time telecom data, you have the data packets, you have the industrial processing, you have the voice, audio, video, voice, router control, all the telecom data you need to process in real time. To process in real time, you need a powerful HPC system which has got many GPUs, many CPUs, many vector processing. Combining all the things, you run the AI application on the thing. So what does it mean? Real-time responsive architecture of HPC is required to process this kind of data. That's the reason today for financial transactions we use mobile. When you get up, we use the mobile. For telecom, we use the mobile. For banking, we use. For reservation, we use. That means what? All amount of data we need to process in real time. So that way, that's where the algorithms. So quickly, I wanted to convey that all the telecom data, we need to develop mathematical models. We need to have a graph theory representation. We need to understand traffic analysis. We need to understand automation techniques. And we need to address the large amount of data. Because if major event happens in your colony, you get lot of telephone calls going and coming. If there is any catastrophe happens, maybe 2 days ago, Delhi, there was a stampede happened in the railway station. Lord, so many phone calls will go, so much amount of data moves. That means called burst traffic data. How do you simulate? So what I'm trying to tell you is that telecom application, weather application, as well as the, if you see, next generation banking sector, finance industry, railways, all these things are very important from economic entry. But data is very used. If you take weather simulation, maybe oil industry application, maybe structural analysis application, maybe dam applications, that is scientific computing. And now the banking, finance, railways are the enterprise national main pillars of economic computing. All these things require back-end high-performance computing. And high-performance computing, we need AI because the data is very used and data is distributed. Data is very complex, heterogeneity. So that means what I covered today, I can quickly tell you. If you see this one, how the telecom traffic goes, you have how many routers, how many core routers, how many antennas, and how the supercomputing application is there, how do you really process. Here, all the routers, switches, multiple ports get open, the traffic gets smooth, and then that's how is happening in the going to be future. That means all dynamically, data moves dynamically, you need to control the network and get a solution. So that means what here, traffic engineering, understanding networks, congestion delays, bottlenecks, using some linear programming techniques, optimal routing of telephone calls, how many data pockets. For example, this program is happening in Amlapuram. Institute is in Amlapuram. Amlapuram to Hyderabad, every Friday there is a lot of traffic. And every Sunday night, Hyderabad, Amlapuram traffic. How many phone calls are going? Each phone call requires how many amounts of bytes of data? What is the shortest path to reach the data from Amlapuram to the Hyderabad? What is the origin Amlapuram? Destination is Hyderabad. What is the origin to destination time taken? All these things are real-time applications in HPC. They require a future actually. So I'm just closing. So what I covered today is I did not cover the programming complete anything at all. My colleague before me, she talked very well about OpenMP and MPA everything. What we conveyed is that challenges in the HPC AI, what kind of systems we normally have. One beautiful thing is your laptop with the Ubuntu operating system can do all problems. Every software is open source. And Ubuntu operating system and every laptop will have the GPUs. And now after some time, 2 years, GPU, CPU are available on your single chip so that you get more advantage in the handling memory. So we talked about shared memory, that is laptops. We have talked about the shared memory with GPUs. We did not discuss more about the GPUs. We also discussed about the clusters. Then we also discussed about the challenges in the programming paradigms. And we also discussed about the some kind of applications overview. See, applications means real-time response architecture is required today. That is where the HPC is going to address. Why do you require? Because you have to use AI techniques to solve many of the data science problems. So I also put some references. I already shared my presentation with Dr. Srinivas. And lastly, I sincerely thank BVCI TCS Engineering College, Department of Computer Science for giving opportunity. And I think I shared the presentation with.
Sir, you will provide.
I take a couple of questions.
Audience, please post your questions and directly ask our Dr. V.C.V. Rao, sir.
Yes, sir. Yes.
Any questions? Sir, one question from my side. If you want to establish HPC lab, what kind of configuration systems we prefer, and how much economically, how much budget is required as a institution level?
Do you understand Telugu also?
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
The answer for this question is pindi koddi rotti.
Okay, sir. Okay. Okay.
That means I'll tell you, every system requires GPU.
Okay.
You can have in low end CPUs, that is CPU system is having 2 cores or 4 cores,
Okay.
but you can take very good GPUs. So you can have two nodes. You can have Ethernet, connect them, 2 nodes. That is 2 multi-core systems. Each multi-core system is having 1 GPU or 2 GPU.
Okay.
Other approach is write your program on your laptop with Ubuntu OS. Hire the computing cycles on the cloud. That is also another approach.
Okay. Okay.
Second one is better because first one means you require a lot of applications, more number of users to use it for 3-4 years. After 3-4 years, your problem size becomes very large, systems becomes obsolete.
Okay.
So you need to strike a balance based on your budget and other things, applications. You can mail me, and in this presentation, my address also there. You can mail me, then we will give you more information.
Okay, sir. Thank you, sir. Thank you very much. And on behalf of our Department of Computer Science Engineering and our institute, the Bonaventure Chalmai Institute of Technology and Science, I'm thankful for your wonderful session. We learned a lot with your practical exposure, and even though in the late night also, as you are actively presented wonderful session, sir. Thank you very much. I am thankful to all the participants, even though beginning due to some app issue, I was unable to connect all of you in time. Sorry again from my side, and tomorrow onwards the session will be fruitfully conducted in time, and in time the session will be closed. Thank you, sir. Thank you very much. And I will meet you soon, sir. Thank you, sir. Thank
Sir,
you.
one point I would like to add here, sir. Dr. V.C.V. Rao, sir, this is Usha Devi from UCAK JNTUK. I'm really very happy to see you here, sir. And it's really very motivated session. Actually, the reason is because you have shared a lot of core details of in application point of view. So the telecommunication application also very inner details you mentioned. Actually, I'm not aware of those things actually. So thank you so much, sir, for your wonderful session. Thank you so much.
Usha Devi, madam. Thank you. Thank you very much, madam.
I want to
Thank you
thank
all.
also.
I sincerely
You are like a student. Thank you, ma'am.
thank you all. Shubhratri. Good night.
Thank you, sir. Thank you. Asugar, do you have any doubt? Any
No,
query?
I just want to thank Ushadev gar and CV Rao gar.
Okay,
I
sir.
sincerely appreciate their time and effort which they put in this lecture. It's like they bring us back to the drawing board, but it's very engaging and very good. Yeah, thank you, sir.
Venkataguram is also one of our resource persons from USA. He is vice president from JP Morgan, and his session on the schedule. Okay, thank you, Venkataguram garu.
Thank
And
you.
all the participants. Thank you very much. Okay, with your permission, I am concluding today's. Thank you, sir. Thank you.